Hello everyone, myself Kirti. I am a student of BSc Chemistry Honours final year. This is an audio recorded lecture on the topic fats, oils and detergents. Introduction. Oils and fats are widely distributed in nature, both in animal and plant kingdoms. In animals, they are present under the skin and in muscles, but in plants, they are mainly found in the seeds. Some important examples of fats are butter, lard, tallow, beef, etc. While groundnut oil, cottonseed oil, olive oil, palm oil, coconut oil, sunflower oil, soybean oil, linseed oil, sesame oil, etc. are important examples of vegetable oils. Fats and oils are one of the three major constituents of our food, the other two being carbohydrates and proteins. In fact, fats and oils serves as energy reservoirs for the animals. In human beings, only a few hundred grams of glycogen, that is carbohydrate, can be stored, which can barely supply the body's energy need for about 12 to 18 hours. In contrast, large amounts of fat, that is 12 kg for an average person weighing 70 kg, can be stored, which can apply the body's energy needs for about 8 weeks. Besides this, oil and fats serve as raw material for a number of industries such as soap, paints, varnishes, and vanaspati ghee, etc. Next is natural fats. The fats obtained from animal sources such as butter from milk of cows and buffaloes, lard from hogs, and tallow from sheep, goats, etc. are called natural fats. The name is simply given to differentiate these fats from those fats which are obtained by hydrogenation of oils. Next is edible and non-edible oils. Oils such as groundnut oil, sunflower oil, soybean oil, rapeseed oil or mustard oil, olive oil, sesame oil, which are used for cooking purposes, are called edible oils, while oils such as cottonseed oil, linseed oil, castor seed oil, or mohoma oil, which are used in soap, paints, varnishes, and lacquer industries, are called non edible oils or industrial oils. On the basis of iodine values, oils have also been classified as drying, semi drying, and non drying oils. Industrial oils may include essential oils or mineral oils. Essential oils such as rose oil, jasmine oil, lavender oil, eucalyptus oil, peppermint oil, etc., are volatile oils isolated from plants. Essential oils may be hydrocarbons, alcohols, aldehydes, ketones, esters, but not ester of glycerol, etc. For example, peppermint oil, which is an essential oil, contain menthol, which is an alcohol, as its chief constituent. Essential oils are mainly used in perfumes, cosmetics, and in pharmaceutical products. On the other hand, mineral oil such as paraffin oil is a mixture of saturated and unsaturated hydrocarbon and not esters as triglycerides. They cannot be saponified. They are called oils simply because of their physical appearance. They are non-edible and mainly used as fuels. Next is triglycerides, the composition of oil and fats. As stated above, fats and oils are triesters of glycerol with higher aliphatic monocarboxylic acids. In other words, they are triacyl glycerols and are commonly known as glycerides. Fats and oil may be represented by the general formula which is given here. Next is fatty acids. With only a few exceptions, all the monocarboxylic acids isolated from fats and oils are straight chain compound containing 3 to 18 carbon atoms. Further, with the exception of only C3 and C5 acids, all other acids found in fats and oil contain even number of carbon atoms. The chief saturated fatty acids present in oil and fats are lauric acid, mycetic acid, palmitic acid, and stearic acid. Besides saturated fatty acids, unsaturated fatty acids containing one or more double bonds in cis orientation may also be present in oil and fats. The chief unsaturated fatty acid present in oil and fats are oleic acid, linoleic acid, etc. Next is classification of glycerides. The three fatty acids in glycerides may be same or different. Therefore, glycerides are classified as simple or mixed glyceride according as they have the same or different acid residues. For example, tripalmitin or glyceryl tripalmitate is a simple glyceride, while alpha oleo beta palmito alpha styrene is a mixed glyceride. Glycerides are further classified into saturated and unsaturated glycerides according as they contain saturated fatty acid residue or unsaturated fatty acid residue. For example, tristyrene and triolene. Tristyrene is saturated triglyceride and triolene is an unsaturated triglyceride. Both simple and mixed glycerides are found in natural oils and fats. In fact, oil and fats are complex mixture of mixed glycerides along with small amount of simple glycerides. Chemical difference between oil and fat is the main difference between oil and fat is the proportion of saturated and unsaturated glycerides. Triglycerides with higher proportions of saturated acid residues such as palmitic acid, stearic acid are solid at ordinary temperature and are called fats, while those with higher proportion of unsaturated acid residue such as oleic acid, linoleic acid, etc. are liquids at ordinary temperature and are called oils. Next is melting point of glycerides. As stated above, fatty acids have one or more double bonds having less stable cis stereochemistry. For example, oleic acid has one cis double bond at C9. Linoleic acid has two double bonds at C9 and C12, while linoleic acid has three cis double bond at C9, C12 and C15 position. These cis double bonds have vital biological importance. In the solid state, the molecule of saturated fatty acid fit closely in the crystal lattice due to their zigzag tetrahedral structures. On the other hand, cis unsaturated fatty acids have a bend at the double bond and hence do not fit closely, thereby lowering their melting points. Next is their chemical properties. Fats and oils, being triesters of glycerol, show all the reaction of simple esters. In case the glycerides contain unsaturated fatty acid residue, they also show the usual addition and oxidation reaction of alkenes. Some important reaction of fats and oils are given below. First is hydrolysis. Fats and oils are readily hydrolyzed by treatment with superheated steam, mineral acids or alkalis. Hydrolysis by superheated steam or mineral acid give a mixture of fatty acids and glycerol. However, when the hydrolysis is carried out by alkalis, glycerol and salts of fatty acids are formed. Since the salt of higher fatty acids thus formed are used as soap, the alkaline hydrolysis is commonly called saponification. In the digestive system of human being and animal, fat and oils are hydrolyzed to glycerol and fatty acids by a number of enzymes called lipases. Next reaction is hydrogenation. Oils which contain a higher proportion of unsaturated glycerides add on hydrogen in the presence of finely divided nickel as catalyst to form solid fat. For example, triolene react in the presence of nickel at 453 Kelvin temperature to give tristyrene. The process is called hydrogenation or hardening of oil. It is similar to catalytic hydrogenation of alkenes and involves the reduction of double bond present in unsaturated glycerides to form saturated glycerides. This process is extensively used for the manufacture of vanaspati ghee such as dalta, rath, gagan, etc. from groundnut, peanuts, sunflower and other edible oils. Hydrogenation is never carried out to completion but is stopped as soon as fat of consistency comparable to ghee is obtained. The completely hydrogenated fats are too hard to be useful as kitchen shortenings. The main advantage of hydrogenation is that as compared to oil, fats have better storage qualities and do not become rancid easily. Next reaction is hydrogenolysis, that is conversion to alcohols. Fats and oils on treatment with hydrogen at high temperature and pressure in the presence of copper chromate, that is CuCr2O4, as catalyst undergo reductive cleavage to form glycerol and long chain aliphatic alcohols. This splitting of a fat or an oil to glycerol and a higher long chain alcohol by hydrogen is called hydrogenolysis. The long chain alcohol thus produced are used for the manufacture of synthetic detergents. Next reaction is transesterification. Fats and oils can be converted into simple esters of carboxylic acid such as methyl, ethyl esters, etc. by transesterification. It involves the treatment of a fat or an oil with a large excess of a suitable alcohol in presence of acidic or basic catalyst. The process of transesterification is quite useful for the large scale preparation of long chain fatty acids and long chain primary alcohol of high purity. For this purpose, the mixture of methyl esters obtained by transesterification is subjected to fractional distillation to separate the individual ester. These upon hydrolysis yields fatty acids of high purity. Alternatively, the individual methyl esters are reduced to get long chain primary alcohols. Next reaction is addition of halogens. Like alkenes, unsaturated glycerides add halogen across the double bond to form addition product. The addition of iodine is usually carried out by treating the fat or the oil with iodine in presence of mercury chloride as catalyst. Since the amount of iodine used is proportional to the number of double bonds present, therefore this reaction is used for determination of extent of unsaturation in a given fat or the oil. Next reaction is rancidity. When fats and oils are exposed to warm air and moisture for a long time, they develop a disagreeable smell and taste. This process is called rancidity and involves the hydrolysis of esters to chain to produce fatty acids and oxidation at double bonds to form short chain acids and aldehydes. These short chain acids and aldehydes are volatile and have offensive smells. Therefore, they impart unpleasant odor to oil and fat. Rancidity is of following two types. First is hydrolytic rancidity. This type of rancidity is caused by the liberation of lower fatty acids by hydrolysis of triglycerides. For example, when butter is exposed to warm air and moisture, the hydrolysis of the glycerides in butter yield butyric acid and other volatile acid like caproic, caprilic, capric, etc. with unpleasant odor. This process of hydrolysis is catalyzed by enzymes which are produced by the microorganisms present in air. This type of hydrolytic rancidity can, however, be checked by keeping the butter covered in a refrigerator. Next is oxidative rancidity. This type of rancidity is caused by oxidation of the unsaturated triglycerides by air to form short chain acids and aldehyde having unpleasant smell. It is believed that first the ester linkage are hydrolyzed to yields unsaturated acid which undergo oxidation at the site of double bond to produce short chain acids and aldehydes. For example, oleic acid undergoes oxidation to form pelargonic acids and azelaic acids. Oxidative rancidity can be prevented by the addition of certain chemicals called antioxidants. Two antioxidants which occur in the natural fats are vitamin C and vitamin E. Next is analysis of fats and oils. Fats and oils are extensively used in a number of industries, therefore, it is essential to check the quality of a given fat or an oil. This involves the determination of physical constant such as melting point, specific gravity, refractive index, etc., and chemical constants such as acid value, iodine value, saponification value, Richard Missel value, etc. Some important chemical constants are described below. First is acid value. It is defined as the number of milligrams of potassium hydroxide required to neutralize the free fatty acids present in 1 gram of a fat or an oil. The acid value is determined by dissolving a known weight of the given fat or the oil in pure neutral alcohol and titrating against standard KOH solution using phenolphthalein as indicator. The acid value is a measure of free acid present in a given fat or oil. A high acid value indicates that the given sample of the fat or oil is quite old and has become rancid. Next is saponification value. It is defined as the number of milligrams of potassium hydroxide required to completely saponify 1 gram of the fat or oil. In other words, it represents the amount of potassium hydroxide in milligrams required to neutralize the fatty acids formed as a result of completely hydrolysis of 1 gram of the fat or oil. Saponification value is determined by refluxing a weight quantity of the fat or oil with a known excess of standard alcoholic potassium hydroxide solution and then titrating the unreacted alkali against a standard acid. For example, saponification value of trialurate and tripalmitin can be determined as given. Thus, the saponification value gives an idea about the molecular weight of the fat or oil. Obviously, smaller the saponification value, higher is the molecular weight. For example, tripalmitin, which has molecular weight 806, has a saponification value of 208, whereas trialurate with molecular weight 638 has a saponification value of 263. The saponification value also indicates the length of carbon chain of the acid moiety present in the oil and fat. The higher the saponification value, greater the percentage of short chain fatty acids in the glycerides of the fat or oil. Butter with short chain fatty acids have saponification value between 210 to 230, whereas soybean oil has saponification values between 189 to 195. Next is iodine value. It is defined as the number of grams of iodine that will combine with 100 gram of the fat or oil. Iodine value may be determined by any one of the following two methods. First is Hubble's method. In this method, a solution of a known weight of the fat or oil in CCl4 is allowed to react with a known excess of a saturated solution of iodine in ethanol in presence of mercury chloride as catalyst. The unreacted iodine is then determined by titrating it against standard sodium thiosulfate solution using starch as indicator. Second is Witt's method. In this method, a solution of more reactive iodine monochloride in glacial acetic acid is used in place of iodine and mercury chloride. A known weight of the oil or fat is dissolved in CHCl3. Witt's solution is then added. Iodide chloride adds across the double bond. The iodide chloride left unused is then treated with potassium iodide solution to liberate an equivalent amount of iodine. The liberated iodine is then titrated against hypo solution using starch as indicator. The amount of iodine monochloride that has added across the double bond is then determined using the following relation, that is iodine value is equal to V1 minus V2 into N into 12.7 divided by W, where V1 is volume of hypo used for blank titration, V2 is volume of hypo used for unreacted iodide monochloride, N is equal to normality of hypo solution, and W is equal to weight of oil or fat taken. Iodine value is a measure of the extent of unsaturation present in an oil or fat. The higher the iodine value, the more unsaturated is the oil or the fat. Next is Richard Missile value, that is RM value. It is defined as the number of milliliters required to neutralize the steam volatile fatty acids obtained by completely hydrolysis of 5 gram of fat or oil. To determine the RM value, a known weight of the fat or oil is completely saponified with alkali. The resulting solution is acidified with dilute H2SO4 and then subjected to steam distillation. The distillate, which contains the volatile acid, is then titrated against 0.1 normal KOH solution. The RM value is then calculated as follows. RM value is equal to volume of 0.10 normal KOH used for neutralization into 5 divided by weight of the fat or oil taken. Next is industrial oil of vegetable origin, that is drying oils. Certain oils such as linseed oil, tung oil, etc., when exposed to air in thin layers, form hard and tough water insoluble solids. The process is known as drying, and such oils are called drying oils. Oils like olive oil, groundnut oil, etc., which do not dry on exposure to air, are called non drying oils, and those which dry slowly, such as cottonseed oil, are called semi drying oils. Chemically, drying oil contain a high percentage of unsaturated glycerides as shown by their high iodine value. On the other hand, non-drying oil have low iodine value while semi-drying oils have intermediate iodine value. For example, drying oil have iodine value above 150, non-drying oil have iodine value less than 100, while semi-drying oil have intermediate iodine value, that is 105 to 114. Unsaturated glycerides contain linoleic acid and linoleic acid as the unsaturated fatty acid residue. These acids contain 2 and 3 isolated double bonds respectively. In general, drying oil containing unsaturated glycerides with conjugated double bonds dry more rapidly than those containing isolated double bonds. Drying oils are used as a medium for paints, varnishes, and lacquers. In fact, paints are suspension of some pigments or the organic coloring matter in linseed oil to which some turpentine oil has been added as a thinner. When these paints are applied on any wooden or iron surface in thin layers, they quickly dry up to form a tough organic film which protect the surface being painted. Mechanism: the actual process of drying does not simply involve removal of moisture or evaporation of solvent but involve complex changes. It is believed that the reactive allylic hydrogens present in unsaturated glycerides are first attacked by oxidation to form hydroperoxy compounds, which then combine with the allylic hydrogen of the other glyceride molecule, forming peroxide bridges. The monomer molecule thus obtained subsequently undergo polymerization to form a tough network solid. The whole process is the mechanism of drying. This is the diagram which show the mechanism. Next is soap. Substance like soap and synthetic detergent which concentrate at the surface of the solution or interfaces form surface films, reduces surface tension of the soil and help in removing dirt and dust by emulsifying grease are called surface active agent or surfactants. The molecule of a surfactant contain two characteristics group, one of which is water soluble, that is hydrophilic group, and other is oil soluble, that is lyophilic or lipophilic group. Soaps are sodium or potassium salts of higher fatty acids such as palmitic acid and oleic acid. These soaps are generally obtained by the hydrolysis of oils and fats with aqueous alkalis. The process is called saponification of oil and fats. The fats and oils commonly used for soap manufacture are tallow, lard, olive oil, linseed oil, mahua oil, rapeseed oil, coconut oil, and palm oil. Soaps containing 12 to 18 chain atoms have good cleansing action. Soap with 12 carbon atom are comparatively soluble in water, whereas soap containing 18 to 22 carbon atoms are not useful as soap because of their insolubility in water. Sodium soaps are generally hard and hence are called hard soaps. These are used for washing of clothes. Potassium soaps, on the other hand, are more expensive and produce a softer leather and hence are called soft soap. They are used for making shaving creams, shampoo, liquid soaps, etc. Transparent soaps are prepared by dissolving ordinary soap in alcohol and removing the insoluble part by filtration. Evaporation of alcohol leaves behind transparent mass. Soaps are 100% biodegradable, that is, microorganisms present in sewage water can completely oxidize soap into CO2. As a result, it does not create any pollution problem. However, soap have two disadvantages. First is soap cannot be used in hard water since calcium and magnesium ion present in hard water produce curdy white precipitate of calcium and magnesium soaps. Second is soaps cannot be used in acidic solution since acid precipitate the insoluble free fatty acids which adhere to the fabrics and thus block the ability of soaps to remove oil and grease from fabric. Next is synthetic detergent. These days, in place of soap, the substances which are being largely used as cleansing agent are synthetic detergent. As the name suggests, they are obtained from pure synthetic chemicals as compared to soaps, which are derived from chemicals which are obtained from natural sources like oils, fats. In fact, synthetic detergents are sodium or potassium salts of long chain alkyl hydrogens, sulfates, or aryl sulfonic acids. Unlike soaps, synthetic detergent can also be conveniently used even in hard water. This is due to the reason that calcium and magnesium salt of detergent, like their sodium or potassium salts, are insoluble in water. Hence, synthetic detergent do not form curdy white precipitates with hard water. Further, they can also be used in acidic solution. However, synthetic detergent have only one disadvantage. Unlike soaps, they are not completely biodegradable and hence cause water pollution. Synthetic detergents are of three types. First is anionic detergents. They are so called because a large part of their molecules are anions. These are of two types. First is alkyl sulfates. They are obtained from long chain alcohols by treatment with concentrated H2SO4 followed by neutralization with NaOH. Some important example of this type of detergent are sodium lauryl sulfate and sodium stearyl sulfate. Sodium lauryl sulfate is called sodium dodecyl sulfate SDS and is used in shampoos and cosmetics. Second is alkyl benzene sulfonates. These are obtained by conversion of benzene into long chain alkyl benzene followed by sulfonation and neutralization with NaOH. The most widely used domestic detergent is the sodium P-N deodecyl benzene sulfonate. Alkyl benzene sulfonates, in which the phenyl group is either attached to the end of the long alkyl chain or any other secondary position, have high biodegradability and hence are called soft detergent, while alkyl benzene sulfonates having branched chain alkyl groups have poor biodegradability and hence are called hard detergents. To differentiate this detergent on the basis of biodegradability, alkyl benzene sulfonates having long straight chains such as sodium PND-decyl benzene sulfonate and sodium 2-deodecyl benzene sulfonate are called LAS detergent, while those having branched chain are called ABS detergents. An important example of ABS detergent is given here. Next type of detergent is cationic detergent. These are quaternary ammonium salts containing one or more long chain alkyl groups. They are called invert soap because their surface activity is due to positive ion and not to a negative ion, as in alkyl hydrogen sulfate detergent. Being more expensive than the anionic detergent, they found limited use. Besides being good cleansing agent, they possess germicidal property and therefore they are widely used as germicides in hospital. Next type of detergent is non-ionic detergent. These are esters of high molecular mass alcohol obtained by reaction between polyethylene glycol and stearic acid. These may also be obtained from long chain alcohols by treatment with excess of ethylene oxide in presence of a base. Like alkyl sulfates, ethoxylates are also biodegradable. Next is composition of a detergent cake. A cake of detergent containing about 20% of active detergent and an equal amount of sodium sulfate to make up the bulk of the powder. A further 30 to 50% of sodium triphosphate or STPP is added as an additive. Other ingredients include sodium perborate, which act as the bleaching agent, some optical brighteners or fluorescents, that is organic compound which make yellow clothes appear white, and some foaming agents. Next is detergent pollution. Detergent having branched chain hydrocarbon cause pollution in rivers and other waterways. The reason being that side chain soap bacteria from attacking and breaking the chains. This result in slow degradation of detergent molecule leading to their accumulation since are more prone to attacked by bacteria. Therefore, in most of the detergent used these days, the branching is kept to a minimum so that the detergent become easily biodegradable and pollution is prevented. Next is cleansing action of soap and detergent. All the soap and detergent contain two characteristics group, hydrophilic and lyophilic group. As a result, one end of the molecule of a soap or detergent tends to go into oil phase and other end tends to go into the water phase, with the net result that the material concentrate at the surface of the solution or interface. The dirt is generally held to a dirty surface by a thin film or of an oil or grease. When the dirty surface is treated with soap solution, the non-polar hydrocarbon chain of the soap or detergent dissolve in oil or grease, and the carboxylate group of the soap or the sulfonate group of the synthetic detergent is held by surrounding water. This lowers the surface tension between water and grease. As a result, a stable emulsion of oil in water is formed. When the surface or the cloth is mechanically scrubbed, the loosened dirt particles are absorbed by colloidal soap or detergent particle in the ultimate washed away. So this is all for today's video. Thank you.